The sudden, sharp sensation of a metallic taste in the mouth, often triggered by a small accidental injury to the lip or gums, is not a trick of the nervous system or a sensory illusion, but a direct encounter with the elemental reality of the human body. This distinct copper-like tang is the physical signature of iron, a metal that serves as the most critical structural component of human life. While the common perception of iron is associated with the cold, unyielding surfaces of industrial machinery, heavy frying pans, or the massive skeletal frames of urban skyscrapers, the most vital manifestation of this element is microscopic and biological. Within the average adult body, there are approximately 4 to 5 grams of iron circulating through the veins and stored in the tissues. To visualize this quantity in an engineering context, if all the iron atoms were extracted from a single person and forged together, the result would be a single, substantial industrial nail. This small, concentrated mass of metal is the only reason the biological machine can function, serving as the essential anchor for the transport of oxygen from the atmosphere to the most distant cells of the brain. The exploration of these hidden foundations of life and the cosmos is a journey into the very architecture of existence. Contributing to this ongoing research by subscribing to the channel and leaving a detailed comment below helps to maintain the flow of high-level scientific inquiry for a global audience. The iron within the human body does not exist in a free, metallic state, which would be toxic and unmanageable, but is instead carefully caged within complex protein structures. The most famous of these is hemoglobin, a sophisticated transport protein that occupies the interior of red blood cells. To understand the operation of hemoglobin, one should look at it as a specialized fleet of 4-seated courier vehicles. Each vehicle, a single hemoglobin molecule, contains 4 iron atoms at its core, each held within a specialized molecular ring called a heme group. These iron atoms act as chemical magnets, possessing a specific electromagnetic affinity for oxygen molecules. When blood passes through the lungs, where the concentration of oxygen is high, the iron atoms in the hemoglobin form a temporary, reversible bond with the oxygen. This is not a permanent weld, but a delicate, tactical embrace. As the blood travels through the body to tissues where oxygen is scarce and carbon dioxide levels are rising, the chemical environment changes, causing the iron to relax its grip and release the oxygen where it is needed most. The color of human blood is a direct consequence of this interaction between iron and oxygen. In a laboratory or industrial setting, the reaction of iron with oxygen in the presence of H2O is known as oxidation, or more commonly, rusting. In the human body, a similar process occurs, though it is strictly controlled by the surrounding proteins to prevent the metal from damaging the cells. When the iron in hemoglobin is bound to oxygen, it absorbs specific wavelengths of light and reflects others, resulting in a vibrant, bright red hue. This is why arterial blood, freshly charged from the lungs, is strikingly crimson. Conversely, when the iron has surrendered its oxygen and is returning to the heart through the veins, its molecular shape shifts slightly, changing the way it interacts with light and resulting in a darker, more purplish tone. The flush of a healthy person's cheeks is, quite literally, the visible evidence of trillions of iron atoms rusting and unrusting in a continuous, high-speed cycle every second of every day. The efficiency of this system is an evolutionary masterpiece. For most of Earth's early history, life utilized different elements for energy transport. Some ancient organisms, and even modern creatures like the horseshoe crab, utilize copper-based proteins called hemocyanin, which results in blue blood. However, for the high energy demands of mammals and birds, iron became the preferred choice because of its unique ability to switch between different oxidation states, specifically iron +2 and iron +3. This flexibility allows iron to move electrons with remarkable speed and precision. Beyond just carrying oxygen, Iron is an essential component of the electron transport chain, the biological power plant located within the mitochondria of every cell. Here, iron-rich enzymes act as a series of microscopic stepping stones, allowing electrons to hop from one station to the next to create ATP, the universal currency of biological energy. Without those 5 grams of iron acting as a conductive bridge, the body would be unable to convert food into movement or thought, leading to a total systemic shutdown. Because iron is so potent and essential, the body treats it as a precious and dangerous commodity, employing a rigorous system of recycling and storage. Unlike many other nutrients, the body has no active mechanism to excrete excess iron, so it manages the supply with extreme care. When a red blood cell reaches the end of its 120-day lifespan, it is not simply discarded. Specialized scavenger cells, known as macrophages, break down the old cell and carefully extract the iron atoms, stripping them from the heme group and handing them over to a transport protein called transferrin. This protein acts like a secure armored truck, carrying the iron through the bloodstream to the bone marrow, where it is immediately incorporated into new red blood cells. To prevent any stray iron from causing oxidative damage while it is being stored, the body uses a storage vault called ferritin. This is a hollow spherical protein that can hold up to 4,500 iron atoms in a non-reactive, mineralized form. It is a biological warehouse, ensuring that the __3__ of the body is always available for duty, but never allowed to run wild. The consequences of even a slight imbalance in this iron management system are profound. In the condition known as iron deficiency anemia, the body loses its ability to produce enough hemoglobin, resulting in a decline in the blood's oxygen-carrying capacity. On a physical level, this is like trying to run a massive industrial factory while half of the delivery trucks are missing. The system slows down, energy levels drop, and the brain functions in a state of perpetual __4__. At the other end of the spectrum, a condition called hemochromatosis occurs when the body absorbs too much iron, leading to the metal accumulating in the liver, heart, and joints. In these cases, the __5__ potential of iron becomes literal, as the excess metal triggers the formation of free radicals that tear through cellular membranes like microscopic shrapnel. The history of our understanding of this internal metal is a story of transition from mystical observation to mechanical precision. For centuries, the link between the metallic taste of blood and the strength of the body was noted by soldiers and healers. But it was not until the 18th century that chemists began to isolate iron from human remains. In 1747, the Italian scientist Vincenzo Menghini demonstrated the presence of iron in blood by showing that the ash from burnt blood could be attracted to a magnet. This was a revolutionary moment in human self-perception. The realization that we are not composed merely of __6__ biological tissue, but are reinforced by the same elements that forge the crust of the Earth. This internal iron is not just a biological coincidence, but a direct link to the physical history of the planet. Every atom of iron in a human's veins was once part of the Earth's mantle or crust, absorbed by plants from the soil and passed up the food chain. The iron we consume in a steak or a bowl of spinach is a fragment of the planet itself, repurposed to act as the respiratory engine for a sentient being. We are, in a very real sense, walking, talking extensions of the Earth's geology, utilizing the most stable and reliable metal in the periodic table to maintain the fragile, high-energy state of life. This biological rebar provides the structural integrity and the energetic potential that allows life to exist in an oxygen-rich atmosphere. As we transition from the domestic and biological scale to the cosmic scale, it becomes clear that iron is not just the architect of our bodies, but the ultimate arbiter of the fate of the stars themselves. The same properties that allow iron to bind oxygen in the lungs are the very properties that make it the most dangerous and final element in the life of a sun. The 5 grams of metal that provide the right to breathe are the same material that, in a distant part of the galaxy, act as a stellar killer, marking the end of the atomic ladder and the beginning of a cosmic collapse. The existence of iron across the cosmos is the result of a profound thermodynamic boundary that dictates the lifespan of every massive star in the universe. While elements like hydrogen and helium are the primary fuels of the celestial furnace, iron represents the terminal point of the atomic ladder, a substance that does not contribute to the life of a star, but serves as the physical catalyst for its destruction. In the standard model of stellar evolution, a star maintains its structural integrity through a delicate equilibrium between 2 opposing forces: the inward pull of gravity, which seeks to crush the star into a singular point, and the outward pressure of nuclear fusion, which pushes against that gravity with the force of billions of continuous atomic explosions. For the vast majority of a star's life, this balance is stable. However, the introduction of iron into the stellar core represents a quote 9 that renders this equilibrium impossible to maintain. To understand why iron acts as a quote 10, one must examine the specific binding energy of the atomic nucleus. This can be explained through a quote 11 analogy of energy. When a star fuses light elements like hydrogen into helium, the resulting nucleus is slightly lighter than the sum of its parts. This missing mass is converted into a massive surplus of energy, a process governed by the principle that mass and energy are interchangeable. This surplus acts as a quote 12 that the star uses to pay its quote 13, providing the heat and pressure necessary to hold up the weight of its outer layers. As the star ages and exhausts its hydrogen, it begins to fuse heavier elements: helium into carbon, carbon into neon, and neon into oxygen. Each step of this process continues to yield an energy profit, though the margins become increasingly thin as the atoms become more complex. This progression continues until the star reaches the silicon burning phase, which occurs at temperatures exceeding 3 billion degrees Kelvin. In this high-energy environment, silicon atoms are fused into sulfur, argon, and eventually iron-56. This is the moment where the star's _14_14_ of fusion permanently collapses. Iron-56 possesses the highest binding energy per nucleon of any element in the periodic table. In practical terms, this means that the nucleus of iron-56 is the most stable arrangement of matter possible. Fusing iron into a heavier element, such as cobalt or nickel, does not release energy. Instead, it consumes it. The star, which has spent millions of years generating an outward push from the energy surplus of fusion, suddenly encounters a material that requires an external energy input to react. The transition from a silicon core to an iron core is the final act in the star's life, and it occurs with a speed that contrasts sharply with the millions of years of previous evolution. Once the iron core begins to form, the star has only a few hours, or in some cases, seconds, left to exist. Because iron fusion absorbs energy rather than producing it, the outward pressure that was holding up the star's massive weight simply vanishes. This is equivalent to the sudden removal of the support pillars in a skyscraper. The core, no longer able to support the trillions of tons of gas pressing down from the outer layers, undergoes a catastrophic gravitational collapse. The physics of this collapse are extreme. The core, which may be the size of the Earth, shrinks to the size of a city in a fraction of a second. with the material falling inward at approximately 25% the speed of light. As the density increases, the electrons and protons in the core are crushed together with such force that they merge to form neutrons, releasing a massive burst of neutrinos. This process is known as neutronization. When the core reaches the density of an atomic nucleus, it can no longer be compressed. The infalling outer layers of the star hit this ultra-dense, rigid core and bounce off it, creating a colossal shockwave that travels outward. This is the supernova explosion, one of the most violent events in the known universe. It is during this explosion that the star's inventory of iron, along with the heavier elements created in the heat of the blast, is scattered across the interstellar void. The iron that constitutes the Earth's core, the steel in modern infrastructure, and the hemoglobin in human blood is the literal ash of these ancient, suicidal stars. Without the specific nuclear properties of iron-56 that cause it to act as an energy sink, these massive stars would not explode in such a spectacular fashion. They might simply fade away. Instead, iron ensures that the star ends its life by distributing its heavy elements into the vacuum of space, providing the raw materials for the formation of new solar systems and rocky planets. We are effectively living in the wreckage of a cosmic structural failure. When the early solar system began to form from a rotating cloud of gas and dust 4.6 billion years ago, it was heavily enriched with the iron shrapnel of previous supernovae. Because iron is a heavy and dense element, it played a crucial role in the gravitational sorting of the infant Earth. As the planet formed and was heated by radioactive decay and constant collisions, it became a molten ball of liquid rock and metal. In this liquid state, gravity performed a massive separation of materials based on their density. The iron, being significantly heavier than the silicates that make up the Earth's mantle, sank toward the center of the planet in a process called iron catastrophe. This was not a slow leak, but a massive migration of billions of tons of metal through the interior of the young Earth. The result of this migration is the Earth's core, a two-part structure consisting of a solid inner core and a liquid outer core, composed almost entirely of iron and nickel. The temperature at the center of this iron heart is estimated to be approximately 10,000 degrees Fahrenheit, roughly the same temperature as the surface of the Sun. The pressure is so immense, over 3 million times the pressure at sea level, that the iron in the inner core is forced into a solid state, despite the extreme heat. The outer core, however, remains a swirling, turbulent liquid. The existence of this liquid iron outer core is the only reason the Earth is a habitable planet. Through the principles of magnetohydrodynamics, the movement of the conductive liquid iron creates a massive dynamo effect. As the Earth rotates, the flowing iron generates a powerful magnetic field that extends thousands of miles into space. This magnetosphere acts as a planetary shield, deflecting the solar wind, a stream of high-energy charged particles emitted by the Sun. Without this iron-generated magnetic field, the solar wind would gradually strip away the Earth's atmosphere, just as it did on Mars, which lost its internal magnetic dynamo billions of years ago. The air we breathe is held in place by the protective influence of a spinning ball of iron, located 1,800 miles beneath our feet. The irony of iron's cosmic and geological role is that it is the ultimate element of stability and destruction. At the nuclear level, it is the most stable atom, refusing to release any more energy through fusion, which in turn causes the most violent explosions in the universe. On a planetary scale, its density and magnetism provide the conditions necessary for life to emerge and survive. On a biological level, it is the carrier of the oxygen that powers our thoughts and movements. To look at a simple iron object, a hammer, a nail, or a support beam, is to look at a substance that has traveled through the most extreme environments the universe can provide. It was forged in the high-pressure death gasps of a giant star, survived a journey through the vacuum of space at nearly relativistic speeds, and then navigated through the molten interior of a forming planet to settle in its core and its crust. It is a material that dictates the laws of life and death on every scale, from the subatomic to the galactic. The __20__ is not an antagonist in the cosmic story, but the final arbiter of how energy is recycled throughout the universe, ensuring that the death of one star provides the iron foundation for the birth of a world where complex life can finally look back and understand its own metallic origins. The history of human interaction with iron is a narrative of technological frustration, accidental discovery, and a slow transition from viewing the metal as a divine gift to recognizing it as an industrial commodity. Long before the first mines were carved into the Earth's crust, iron existed in the human world as a rarity of celestial origin. For the civilizations of the Bronze Age, iron was not a material for common tools, but a substance of immense prestige, literally falling from the atmosphere in the form of meteorites. These nickel-iron alloys, forged in the vacuum of space, arrived on Earth in a metallic __21__ state that required no smelting. In the tomb of the Egyptian pharaoh Tutankhamun, archaeologists discovered a dagger of extraordinary craftsmanship. Its blade remains untarnished after 3,300 years. Scientific analysis using X-ray fluorescence spectroscopy has confirmed that the nickel-to-cobalt ratio in the blade's metal matches the composition of the Karga meteorite found in the Nile Valley. During this era, iron was referred to by the Hittites and Egyptians as the metal from heaven, and its value was calculated at approximately 10 times that of gold. It was a material for the gods and kings, a geological anomaly that stood in stark contrast to the soft, terrestrial copper and tin that defined the age. The transition from this celestial jewelry to a practical, terrestrial tool was delayed for centuries by a fundamental barrier of thermodynamics. To understand the difficulty of the early Iron Age, one must compare the melting points of the era's primary metals. Copper melts at 1,984 degrees Fahrenheit, and tin melts at a mere 450 degrees Fahrenheit. These temperatures were achievable in the relatively simple pottery kilns of the ancient world. However, pure iron requires a temperature of 2,800 degrees Fahrenheit to reach its liquid state. For thousands of years, this temperature was physically impossible to maintain with the technology of the time. Ancient smiths could not quote 24 iron into molds like they did with bronze. They had to settle for a process that was more akin to baking a loaf of bread than casting a statue. This early method utilized the structure known as a bloomery, a chimney-like furnace made of clay and stone. The smiths would lay a charcoal and iron ore, typically in the form of iron oxides found in riverbeds or bogs. As the charcoal burned, it produced carbon monoxide, CO, which stripped the oxygen away from the iron ore. However, because the furnace could not reach the melting point of iron, the metal never turned into a liquid. Instead, it formed a _25, a spongy, glowing mass of solid iron mixed with stony impurities known as slag. The engineering challenge of the early Iron Age was not just finding the metal, but physically beating the impurities out of this red-hot sponge using heavy hammers. This created wrought iron, a material that was tough and fibrous but relatively soft. It was a laborious, inefficient process that made iron expensive and limited its use to high-end military equipment. The true _26_ of iron lies in the discovery of its secret partner, carbon. While the goal of the ancient smith was to produce the purest iron possible, pure iron is actually a mediocre material for a sword or a plowshare. It is too soft to hold a sharp edge and prone to bending. The transformation of iron into steel, a material that is both hard and flexible, is a result of the precise management of carbon atoms within the iron's crystalline lattice. Carbon acts as a molecular grit or a spacer. In pure iron, the layers of atoms can slide past one another with relative ease, making the metal soft. When a small amount of carbon, typically between 0.2% and 2.1%, is introduced, the carbon atoms lodge themselves in the gaps between the iron atoms. This creates a structural log jam that prevents the layers from sliding, vastly increasing the metal's hardness. For centuries, this process was governed by ritual and luck rather than science. Smithies noticed that iron kept in contact with charcoal for long periods at high heat became harder. This was the process of carburization, where the iron surface soaked up carbon from the fuel. However, if the iron absorbed too much carbon, exceeding 2.1%, it became cast iron. While cast iron is easy to melt and pour into shapes, it is as brittle as glass. At the microscopic level, the excess carbon forms large, flat flakes of graphite that act like internal cracks. A cast iron sword would shatter upon the first impact with a bronze shield. The history of metallurgy was a long, often bloody search for the middle ground, a material with enough carbon to be hard, but not so much that it lost its structural integrity. The geopolitical impact of mastering this balance was revolutionary. The Hittites, an ancient Anatolian civilization, were among the first to develop the techniques for forging iron on a large scale around 1500 BC. This gave them a significant military advantage, though not for the reasons often assumed. An iron sword was not necessarily sharper than a high-quality bronze sword, but it was cheaper and more sustainable.
Bronze required tin, a rare element that often had to be shipped across thousands of miles from mines in distant Cornwall or Central Asia. Iron, however, is the fourth most common element in the Earth's crust. It is found almost everywhere. Once a civilization unlocked the secret of the bloomery and the carbon balance, they could arm thousands of soldiers instead of just a small elite. Iron was the _quote_33__ metal that allowed for the rise of massive empires and the total reorganization of the ancient map. The drama intensified during the Middle Ages and the early Industrial Revolution with the invention of the blast furnace. By using large, water-powered bellows to force massive amounts of air into the furnace, engineers finally achieved temperatures high enough to melt iron completely. This led to the mass production of cast iron, which was ideal for the cannons that would define European warfare. However, the problem of turning this brittle cast iron into useful, flexible steel remained a bottleneck for global progress. The material that built the first steam engines and the first railways was still largely wrought iron, which required endless hours of manual __34__ and hammering to remove the excess carbon that the blast furnace had introduced. The final breakthrough occurred in 1856 with the Bessemer process, a moment of engineering brilliance that solved the carbon problem through a counterintuitive method. Henry Bessemer realized that the best way to remove the __35__ and excess carbon from molten iron was not to add more fuel, but to blow cold air through it. This seemed like a recipe for cooling the metal, but the chemistry proved otherwise. The oxygen in the air reacted with the carbon and silicon in the molten iron, a process that released an enormous amount of heat. The metal actually became hotter, and the carbon was, quote, 36, as CO2 and CO gases. Within 20 minutes, 30 tons of brittle iron could be converted into high-quality steel. This single invention dropped the price of steel by 80% and provided the raw material for the modern world. The skyscraper, the suspension bridge, and the massive naval vessel. To look at iron through the lens of history is to see a material that has been both a quote 37 and a quote 38. It is a substance that demanded the perfection of human heat management and the deep understanding of atomic scale underscore underscore quote underscore 39 underscore underscore. We moved from scavenging the remnants of a cosmic explosion in the Egyptian desert to building a global civilization on the back of a carbon-controlled iron lattice. The sword, the plow, and the engine are all different manifestations of the same struggle to balance the hardness of carbon with the toughness of iron. The underscore underscore quote underscore 40 underscore underscore of this element is the story of how humanity learned to stop waiting for the sky to fall and started to look into the red-hot heart of the earth to find the strength to build the future. Iron did not just provide the tools for war, it provided the structural skeleton for the modern era, turning the rare quote 41 into the most common and essential framework of human existence. The unseen foundation of contemporary civilization resides far beneath the surface of the planet, in a region where the laws of chemistry and physics operate at pressures and temperatures that dwarf the most extreme industrial furnaces. To understand why a modern metropolis remains powered and protected, one must look 1,800 miles downward to the Earth's outer core. This is a subterranean ocean of liquid iron and nickel, approximately the size of the planet Mars, that is constantly in motion. This movement is not random. It is driven by the internal heat left over from the planet's formation and the radioactive decay of heavy elements. As the Earth rotates, this massive volume of conductive liquid iron churns in great spiral patterns, a phenomenon known as the Coriolis effect. This mechanical motion of a conductive metal creates what physicists call a planetary dynamo. Just as a hand-cranked flashlight generates electricity through the movement of a magnet near a wire, the Earth's core generates a colossal electrical current, which in turn produces a global magnetic field. This magnetic field, or magnetosphere, acts as an invisible atmospheric shield that is the primary reason the Earth remains a lush, H2O-rich world, while its neighbors are barren deserts. Space is not an empty void, but is filled with the solar wind, a relentless stream of high-energy protons and electrons emitted by the Sun at speeds of over 1 million miles per hour. Without the iron dynamo at the center of the Earth, this solar wind would collide directly with our atmosphere, physically stripping away gas molecules in a process called 42. Each solar particle would act like a microscopic billiard ball, knocking oxygen and nitrogen molecules out into the void until the planet was left as a naked, airless rock. The planet Mars provides a grim engineering comparison. Approximately 4 billion years ago, the Martian iron core cooled and solidified, causing its magnetic dynamo to stall. Deprived of its shield, the Martian atmosphere was swept away by the Sun, transforming a once watery world into a frozen wasteland. We are currently breathing and thriving because a spinning ball of liquid iron continues to project a magnetic force field that diverts the solar wind around the planet, like water flowing around the bow of a ship. Beyond this planetary protection, iron is the primary material that allows humanity to manipulate and distribute energy. While copper is the underscore underscore quote underscore 43 underscore underscore that carries electrons, iron is the underscore underscore quote underscore 44 underscore underscore that directs magnetic forces. This utility is based on a property known as magnetic permeability. Most materials, such as wood, plastic, or aluminium, are essentially quote underscore 45 underscore 2 magnetic fields. In contrast, iron is a magnetic sponge. Within a piece of iron,
The atoms are organized into tiny regions called magnetic domains. Under normal conditions, these domains point in random directions, cancelling each other out. However, when an external magnetic field is applied, these trillions of underscore underscore quote underscore 46 underscore underscore align instantly, concentrating and magnifying the magnetic force by a factor of thousands. This specific property of iron is the engine of the electric age. Every modern electric motor, from the tiny vibrator in a smartphone to the massive turbines in a hydroelectric dam, is built around a laminated iron core. In a motor, electrical energy is converted into mechanical movement by using copper coils to create a magnetic field that pushes against a rotor. Without an iron core to focus and direct that magnetic field, the motor would be impossibly weak and inefficient. The iron core acts like a specialized lens, taking a diffuse magnetic quote 47 quote and focusing it into a high-powered quote 48 quote of mechanical force. This allows us to pump H2O to the top of skyscrapers, run the cooling compressors in our refrigerators, and propel the high-speed trains that connect our cities. In the context of the green energy transition, the demand for high-purity electrical steel, a specialized alloy of iron and silicon, is skyrocketing, as it is the only material capable of managing the high-frequency magnetic cycles required by electric vehicle motors and wind power generators. The stability of the global electrical grid is equally dependent on iron's magnetic behavior through the use of transformers. To move electricity across hundreds of miles without losing all of it to heat, the voltage must be stepped up to incredibly high levels, often over 500,000 volts, and then stepped down before it enters a home. This conversion happens inside a transformer, a device that has no moving parts but relies entirely on a heart made of iron. Two separate copper coils are wrapped around a common iron ring. When electricity flows through the first coil, it creates a fluctuating magnetic field in the iron. Because iron is such an efficient conductor of magnetism, it carries that field to the second coil, inducing a new electrical current. To prevent this process from wasting energy, engineers must account for eddy currents, swirling loops of electricity that want to form inside the solid metal, turning the iron into a useless heater. The solution is a masterpiece of precision manufacturing. The iron core is not a single solid block, but is composed of thousands of paper-thin sheets of steel, each coated with an insulating lacquer. This lamination fences in the electrons, preventing the eddy currents from forming while still allowing the magnetic field to flow freely. This allows for an energy transfer efficiency of over 99%. Every light bulb that glows and every computer that runs is a testament to the fact that we have learned to trap magnetic fields inside a laminated iron cage. Furthermore, iron acts as the silent chemical architect of the modern food supply through its role as an industrial catalyst. The Haber-Bosch process, often cited as the most important industrial invention of the 20th century, allows humanity to extract nitrogen from the air to create synthetic fertilizers. Nitrogen molecules, N2, are held together by an incredibly strong triple bond, which is like a three-layered lock that is almost impossible to break at normal temperatures. To feed 8 billion people, we need to break that lock to create ammonia. This is achieved by passing nitrogen and hydrogen gas over a bed of finely divided iron particles at high pressure and a temperature of 850 degrees Fahrenheit. The iron surface acts as a molecular workbench. The nitrogen atoms land on the iron and form temporary bonds with the metal, which loosens their hold on each other. This allows the hydrogen atoms to slide in and bond with the nitrogen, creating the ammonia that forms the base of all modern fertilizer. It is estimated that 50% of the nitrogen atoms in the human body were put there by an iron-catalyzed industrial reaction. Without this specific chemical interaction between nitrogen and iron, the Earth could likely only support about 4 billion people, meaning half of the current human population exists because of an iron workbench in a chemical plant. In the realm of structural engineering, iron, in its refined form as steel, is the only material that possesses the specific balance of tensile and compressive strength required to build upward. A skyscraper is essentially a vertical cantilever that must resist the downward pull of gravity and the lateral force of the wind. Pure iron is too soft for this, but the addition of a small amount of carbon, less than 1%, transforms it into a material that can withstand 50,000 pounds per square inch of pressure. This carbon-iron lattice creates a structural skeleton that can flex without snapping. When a modern skyscraper sways in a 100-mile-per-hour wind, the steel beams are stretching and compressing like giant springs, dissipating the energy of the wind and returning to their original shape. The relationship between iron and modern civilization is therefore one of total integration. It is the material that shields our planet from cosmic radiation, the core that focuses the energy of our motors, the bridge that allows electricity to travel across continents, and the chemical surface that allows us to produce food on a global scale. We do not just use iron. We live within an environment that is shaped and maintained by its unique atomic properties. From the 10,000 degree Fahrenheit liquid at the center of the Earth to the microscopic iron particles in an industrial reactor, this element serves as the hidden engine of our reality. It is the ultimate workhorse of the periodic table, providing the magnetic, structural, and chemical strength that allows a fragile biological species to build a robust, high-tech world. Every time we look at a skyline, flip a switch, or consume a meal, we are benefiting from the precise, predictable behavior of a metal that has transitioned from the heart of a dying star to the heart of our planetary and industrial existence. The structural history of a modern city is a narrative written in a material that is technically in a state of high-energy exile. While we perceive a steel-framed skyscraper or a massive suspension bridge as a permanent monument to human engineering, the iron within these structures is engaged in a constant, relentless struggle to return to its original, more stable state as an oxide. This process, known as corrosion or rust, is not a failure of the material, but a demonstration of thermodynamic equilibrium. Refined iron is a substance that has been forcibly separated from oxygen by the intense heat of a blast furnace, reaching a temperature of 2,800 degrees Fahrenheit. This separation requires an enormous input of energy, effectively stretching the chemical bonds of the metal like a massive industrial-scale rubber band. The moment the iron leaves the factory and is exposed to the H2O and oxygen in the atmosphere, that rubber band begins to snap back. Rust is the physical manifestation of the iron atom finally finding its peace, shedding its high-energy metallic form to become the reddish-brown mineral it was for billions of years before humans intervened. The mechanism of this return is a masterclass in electrochemical destruction. When a drop of H2O lands on an iron surface, it creates a microscopic battery. The water acts as an electrolyte, allowing electrons to flow from the iron to the oxygen. This is a causal chain of decay. The iron atoms lose electrons and become positively charged ions, which then dissolve into the water and react with oxygen to form iron oxide. Unlike copper or aluminum, which develop a tight, protective skin of oxidation that seals the metal underneath, iron oxide is porous and flaky. It acts like a contagious molecular rot. As the first layer of rust forms, it expands and cracks, exposing a fresh layer of iron to the air and water. This cycle continues until the entire structural beam has been leached away, returning to the soil as a fine orange powder. Over a geological timescale, every trace of human architecture, every engine, every rail, and every blade will undergo this reconciliation. Iron is a material that allows us to build the future, but it refuses to let that future be permanent. ensuring that the Earth's crust eventually reclaims every gram of the metal we have borrowed. Yet, as we move beyond the terrestrial life cycle of iron and into the deepest reaches of the future, the element takes on a role of chilling, absolute permanence. In the field of theoretical physics and cosmology, iron is identified as the ultimate state of matter, due to its position at the very bottom of the nuclear energy valley. To understand this concept through a physical analogy, one should visualize a vast, rugged mountain range where every peak represents a different element. Elements like hydrogen and helium are at the highest peaks on one side of the range. They possess a tremendous amount of potential energy that can be released through fusion. Elements like uranium and plutonium are on the high peaks on the opposite side, possessing energy that can be released through fission. Iron 56 sits at the very lowest point of the deepest valley between these two sides. It is the most stable nucleus in the universe because it has no downhill path left to take. It cannot release energy by being smashed together or by being split apart. This nuclear stability leads to a startling conclusion regarding the ultimate fate of the universe. In the extremely distant future, long after the last star has burned out and the black holes have finished their multi-billion-year process of evaporation, the universe will enter the era of iron stars. This is a period projected to occur on a timescale of 10 to the power of 1,500 years, a number so incomprehensibly large that if every atom in the observable universe represented a billion years, it would still not even begin to describe the duration. On this scale, the laws of classical physics are superseded by the slow, inevitable work of quantum tunneling. In a cold, dead universe where the temperature is barely above absolute zero, matter is still subject to the uncertainty principle. On these immense timescales, there is a statistically non-zero probability that the nuclei of any solid matter will spontaneously tunnel through their energy barriers. This process can be explained on the fingers. If you place a ball in a sealed box, classical physics says it will stay there forever. But in the quantum world, if you wait long enough, the ball will eventually appear outside the box without ever passing through the walls. In a dead universe, the atoms in a cold lump of carbon or a frozen gas cloud will eventually tunnel into one another, undergoing a form of cold nuclear fusion. Because iron 56 is the most stable configuration, all matter is gravitationally and thermodynamically destined to become iron. Over decillions of years, the cold remnants of planets, asteroids, and dead stars will reorganize themselves atom by atom until they are transformed into massive, dark spheres of pure, solid iron. These iron stars will be the final outposts of ordered matter in a universe that has otherwise reached a state of total entropy. They will be cold, silent, and incredibly dense, drifting through an absolute void for a period of time that dwarfs the current age of the universe by a factor of trillions. The iron that currently resides in the human bloodstream and in the foundations of our cities is therefore a preview of the end of time. It is the element that defines the beginning of the world by protecting our atmosphere through the planetary dynamo. And it is the element that defines the end of the world by being the final sink for all atomic energy. We are currently living in a brief, high-energy window of history where iron is a tool that we can melt and shape at 2,800 degrees Fahrenheit. We use it to build machines that move and hearts that beat. But this is a temporary state of affairs. The stellar killer that marks the end of a star's life is also the cosmic survivor that will outlast every other material in existence. The story of iron is a journey from the most violent events in the cosmos to the most stable state of reality. It is a material that demands an engineering respect for its power to both create and destroy. Without iron, the Earth would be a radiation-scorched rock without an atmosphere. Without iron, the human body would be unable to harvest the energy of oxygen. And without iron, the universe would have no final destination for its matter. It is the ultimate ascetic of the periodic table, a substance that reaches a point of perfect stability and refuses to change further. When we hold a piece of steel today, we are touching the final answer to the question of what matter wants to be. We are interacting with the ash of the past and the silent, cold substrate of the ultimate future. In the final accounting of the universe, iron is the only element that truly wins the struggle against time. The gold that we covet for its beauty and the lithium we use for our technology are merely transitional states on the long, quantum road toward the Iron Valley. The metallic taste in our mouths is a reminder of our intimate connection to this finality. We are biological entities built around a structural core of iron, living on a planet with an iron heart, in a universe that is slowly, inevitably, turning into an iron graveyard. This is not a dark or mythical fate, but a cold, engineering reality of the laws of thermodynamics. Iron is the architect of the beginning, the sustainer of the present, and the silent monument at the end of eternity. It is the most honest and uncompromising element we will ever know, a material that has already seen the death of stars and will remain to see the death of time itself. Every nail we drive and every breath we take is a brief utilization of the energy that iron is waiting to reclaim. A temporary diversion in a multi-billion-year cycle that leads, inevitably, to the cold, stable peace of the iron star.